Hello everyone, welcome back to the Scientify Talk. Imagine a world where paralysis is no longer a permanent sentence. A world where individuals with spinal cord injuries can walk again, grasp objects, and live independent lives. This might sound like science fiction, but advanced research in neuroscience and technology is bringing this vision closer to reality. For years, spinal cord injuries have been a devastating condition, often leading to permanent paralysis. But now, scientists are developing innovative approaches to restore lost function. One of the most promising avenues is through brain-machine interfaces. In an innovative experiment, researchers at Northwestern University trained a monkey to grasp a ball. They then recorded the brain signals associated with this movement. Amazingly, even after severing the connection between the monkey's brain and its arm muscles, scientists were able to reroute these brain signals directly to the arm muscles, allowing the monkey to grasp the ball once again. This groundbreaking study proved that even with a severed spinal cord, the brain's commands could still be harnessed and redirected to restore movement. Building upon this success, Dr. Miguel Nicolelis, a renowned neuroscientist, has significantly advanced the field of brain-machine interfaces, demonstrating the profound potential of using neural signals to control external devices. One of his groundbreaking experiments involved training monkeys to control a robotic arm using their brain activity. In this experiment, electrodes implanted in the monkey's motor cortices captured their neural signals. These signals were then processed and transmitted to a robotic arm located thousands of miles away in Japan. Remarkably, the monkeys were able to manipulate the arm in real time, demonstrating that thought alone could control a distant mechanical device. This achievement highlighted the potential for BMIs to bridge the gap between the brain and external tools. Dr. Nicolelis' work extended beyond laboratory experiments with animals to life-changing applications for humans. He pioneered the Walk Again project, an ambitious initiative focused on helping paralyzed individuals regain mobility. The project developed an innovative thought-controlled exoskeleton, which allowed patients with spinal cord injuries to walk again. The exoskeleton system utilized a combination of electroencephalogram technology to capture brain signals and translate them into movements of the robotic suit. One of the most inspiring demonstrations of the project's success occurred during the opening ceremony of the 2014 FIFA World Cup in Brazil. A young paraplegic man, outfitted with the thought-controlled exoskeleton, delivered the ceremonial kickoff. The suit was designed to not only move in response to brain signals, but also provide sensory feedback to the user. This feedback, achieved through haptic actuators, allowed the wearer to feel the ground beneath their feet, creating a more natural walking experience. The Walk Again project represented a significant leap forward in neuroprosthetics and rehabilitation technologies. By combining neuroscience, robotics, and engineering, Dr. Nicolelis and his team demonstrated the potential for BMIs to restore mobility and independence to individuals with severe physical disabilities. The research has also inspired ongoing advancements in the field, pushing the boundaries of what is possible in neural interface technologies and offering hope to millions worldwide who live with paralysis. These advancements have translated into remarkable achievements in human trials. Kathy Hutchinson, a quadriplegic, became a symbol of hope when she learned to control a robotic arm with her thoughts using the BrainGate chip, an implanted device that recorded her brain activity. This allowed her to perform tasks like bringing a drink to her mouth, actions she had been unable to perform for over a decade. Another promising approach involves epidural stimulation. In a remarkable study at the University of Louisville, researchers implanted a device near the lower spine of paralyzed individuals to deliver electrical stimulation. This stimulation helped to reactivate dormant neural pathways, enabling some patients to regain partial control over their legs, stand, and even make voluntary movements. These breakthroughs have been made possible by advancements in technology. Neural prosthetics, such as the BrainGate chip, directly interface with the brain to record and transmit neural signals. Exoskeletons, powered by batteries or external sources, provide support and amplify movement, enabling individuals to walk, climb stairs, and even dance. Researchers are also developing neural spinal bridges, which aim to bridge the gap between severed nerves and potentially facilitate the regeneration of damaged axons. While these advancements are truly inspiring, significant challenges remain. Decoding brain signals with high precision is complex and requires ongoing research. Many current solutions require invasive surgeries, which carry risks, and the cost of these advanced technologies can be prohibitive for many patients. However, the future of spinal cord injury treatment is bright, researchers are developing non-invasive methods to record brain activity, such as wearable EEG devices. Combining BMI technology with stem cell therapies and gene therapies holds the promise of repairing damaged nerves and restoring natural neural function. The integration of artificial intelligence is crucial for improving the accuracy and efficiency of BMI systems. The successes of these groundbreaking experiments represent a paradigm shift in spinal cord injury treatment. With continued advancements in neuroscience, engineering, and technology, the dream of restoring full mobility and independence to paralyzed individuals is becoming an increasingly achievable goal. These innovations underscore the incredible potential of interdisciplinary research to transform lives and improve human health. Thank you for watching. If you enjoyed the video, please subscribe, like, and comment. See you next time.